At 6:52 UTC on June 19th, the seafloor off the east coast of Kamchatka, Russia, moved twice in the span of 60 seconds. The United States Geological Survey logged the first event as a magnitude 6, 10 kilometers below the surface. 1 minute later came the second, magnitude 6, and 6 at a depth of 10 kilometers, roughly 136 kilometers east of Petropavlovsk-Kamchatsky, a city of just over 180,000 people. 13 minutes after that, a third event arrived, magnitude 4.9. The European Mediterranean Seismological Center confirmed the same readings within minutes. Less than 24 hours later, on the afternoon of June 20th, the ground moved again, magnitude 5, 8, roughly 220 miles offshore, shallow, felt by residents near the coast. 4 measurable events in under 30 hours, on the same stretch of seafloor. Petropavlovsk-Kamchatsky sits on the edge of the Pacific, a working port city built along a volcanic peninsula that juts down from Russia's far eastern edge, closer to Alaska than to Moscow. At the moment of the second quake, residents reported the now familiar sensation of the ground rolling rather than jolting, a long, slow wave passing under buildings rather than a single sharp strike. Light fixtures swayed. Some residents stepped into the street out of habit, the way people do in a region where shaking has become a known condition of living. No injuries were reported, no structural collapse. The shallow depth of 10 kilometers meant the energy reached the surface quickly, but the magnitude, severe as it was, fell well short of anything resembling the previous summer's event. The United States Geological Survey issued a green alert for both shaking-related fatalities and economic losses, the lowest tier on its color-coded response scale, reflecting a low likelihood of casualties or significant damage given the building stock in the affected area. The Pacific Tsunami Warning Center reviewed the data within the hour and confirmed there was no tsunami threat. This is not, on its own, an unusual notation for this particular patch of ocean. The Kuril Kamchatka subduction zone is one of the most seismically active boundaries on the planet, where the Pacific Plate grinds northwestward beneath the Okhotsk Plate at a rate of roughly 80 millimeters a year, a slow, continuous collision that has built and emptied this fault system many times across recorded history. What makes this particular sequence worth a full report is the calendar. 11 months ago, on the 29th of July 2025, this same stretch of seafloor produced a magnitude 8 earthquake, the 8th largest ever recorded by modern instruments, a rupture so large it sent a tsunami across the entire Pacific Basin, triggered evacuation orders in Hawaii, California, and the Aleutian Islands, and is still, as of tonight, generating aftershocks above magnitude 5 on a near-weekly basis, nearly a full year after the original rupture. The events of June 19th and June 20th are not a new earthquake in a new place. They are the continuing voice of an old one that has not yet gone quiet. We want to be precise about what that means before we go further, because precision is the only thing that separates a report like this from noise. An aftershock sequence, following a megathrust earthquake of magnitude 8, is expected to continue for months, in some cases years, as the surrounding crust redistributes the stress that the main rupture did not fully release. What is being asked by seismologists watching this particular sequence is not whether aftershocks will continue. It is whether the pattern of those aftershocks, their frequency, their depth, their location relative to the original rupture zone is behaving the way the models predicted, or whether something about this sequence is running outside that expectation. Tonight's data is part of answering that question, and we will walk through exactly what the numbers show before this report is finished. We are a Last Light Bureau. Tonight, we are filing a report on what the instruments are recording along the Kuril-Kamchatka Trench, on what 11 months of aftershock data tells us about a megathrust fault that broke catastrophically less than a year ago and has not finished settling, and on what is currently known and not known about how long a sequence like this can run. We will walk through the full seismic record, the original 2025 rupture and the scale of energy it released, the way the United States Geological Survey and the European Mediterranean Seismological Center have tracked the aftershock decay curve in the months since, the way that curve has and has not matched standard expectations for a fault of this size, and exactly what happened in the pre-dawn hours of June 19th and the afternoon of June 20th. Magnitude by magnitude, agency by agency, minute by minute. We will explain how seismic monitoring networks distinguish a true aftershock from an unrelated event on a nearby fault, why depth and location matter as much as magnitude in that determination, and what the current spatial distribution of this sequence tells working seismologists about where the stress redistribution is concentrated. We will also spend time with the historical record of this exact stretch of coastline, because Kamchatka has produced megathrust earthquakes before this one, and the written accounts of those earlier events, some going back nearly 3 centuries, recorded by travelers, missionaries, and early Russian administrators stationed at the edge of the empire, describe sequences with a structure that bears close examination against what the instruments are showing tonight. We will name the events, the years, the witnesses, and the numbers. And we will go further back than the written historical record into territory most outlets covering this story have not touched and will not touch. 3 separate human traditions, each older than seismology as a scientific discipline, each developed independently of the others, on different continents, in different centuries, made specific claims about how the ground behaves when it has been broken open and has not finished moving. One of those traditions comes from the islands directly across the Pacific from where tonight's earthquakes occurred, developed by a culture that has lived with this exact ocean's temperament for longer than written records exist for the region. We are not going to draw any conclusions about that yet. We are simply noting that it exists, and that by the end of this report, we will have laid out exactly what each tradition said, in what language, recorded by whom, under what circumstances, and how the structure of that claim measures against the data currently coming off the seafloor at the Kuril-Kamchatka trench. This is what we do here, every night. We take the measurement that made the news cycle for an afternoon and ask what it would mean to a culture that had been watching this exact patch of earth for 1,000 years, using nothing but memory and consequence to track what their instruments could not yet measure. We are a small operation. We do not have a studio or a widely recognized name, and we are not trying to compete with the channels that get to a breaking story faster than we do. What we have is time, patience, and a standing policy of not reporting anything we cannot trace to a named source. If that is the kind of report you came here for, settle in. This one runs long, the way the real ones always do, and there is a great deal of ground to cover before we are done. Before we begin, tell us where you are watching from tonight. We get a clearer sense of who is sitting up with us at this hour than you might expect, and it helps us decide what to file next, which regions are paying closer attention than others, and which stories are landing with the people who actually live near the fault lines and coastlines we report on most closely. The full record starts now. A magnitude 6. 6 earthquakes struck the seafloor off the east coast of Kamchatka, Russia, at 6:52 UTC, on the 19th of June 2026, at a depth of 10 kilometers, according to the United States Geological Survey. The event was preceded 1 minute earlier by a magnitude 6 earthquake at a depth of 28.4 kilometers, and followed 13 minutes later by a magnitude 4.9 earthquake. The European Mediterranean Seismological Center independently confirmed the magnitude and depth of the lead event within minutes. There is a number buried inside the technical record of this sequence that almost no outlet covering the story today mentioned by name, and we are going to reach it before this report is finished. It concerns the precise relationship between the timing of June 19th's events and a separate threshold that seismologists watching the Kuril-Kamchatka trench have been quietly tracking since roughly the 6-month mark following last summer's mainshock, a threshold that has more to do with the shape of the entire sequence than with any single earthquake's magnitude. We will give you that number, what it measures, and why several of the scientists monitoring this fault consider it more diagnostically useful than the magnitude figures the wire services led with. The epicenter of the lead event sat approximately 136 kilometers east of Petropavlovsk-Kamchatsky, a city of just over 181,000 people, and 151 kilometers east of Yelizovo, a town of roughly 40,700. The German Research Center for Geosciences, known by its German acronym GFZ, logged the same sequence independently, as did the Kamchatkan branch of the Geophysical Survey of the Russian Academy of Sciences, the regional agency responsible for monitoring this specific stretch of the Kuril-Kamchatka trench around the clock. The Pacific Tsunami Warning Center reviewed the data and issued no tsunami threat for the June 19th sequence. The United States Geological Survey's automated pager system, which estimates probable casualties and economic losses within minutes of any qualifying earthquake worldwide, assigned a green alert level to both categories. Its lowest tier, reflecting a low likelihood of significant harm given the offshore location and the building stock in the nearest population centers. Less than 24 hours later, at 3:49 p.m. local time on June 20th, a fourth measurable event struck the same general stretch of seafloor, recalculated by the European Mediterranean Seismological Center from an initial estimate of magnitude 5.5 up to a confirmed magnitude 5.8, at a depth that was itself revised during the assessment window from 32 kilometers to 35 kilometers, with the epicenter location corrected by 16 kilometers toward the south-southeast as additional station data arrived. This is itself a routine and expected part of how seismic monitoring works. The first numbers released after any earthquake are preliminary, generated from a limited number of stations that detected the event within the first several minutes. As more seismic stations report in, and as more sophisticated waveform analysis is run against the initial data, agencies revise their figures, sometimes within minutes, sometimes over several hours. The June 20th event was reported felt by residents near the epicenter, light shaking, consistent with a magnitude in the high fives at a moderate depth. 4 measurable earthquakes, magnitude 4, 9 or higher, in a 30-hour window, on a stretch of subduction zone that produced one of the largest earthquakes in the history of seismic instrumentation less than a year earlier. To understand what that means and what it does not mean, we need to walk back to the original event and to the agencies that have been tracking this fault every day since. To understand what the events of June 19th and 20th represent, the record requires us to go back to the 29th of July 2025 at 23 hours 24 minutes and 52 seconds UTC, which was the morning of July 30th in Kamchatka's local time zone. At that moment, a magnitude 8.8 earthquake ruptured the Kuril-Kamchatka trench at a depth of 35 kilometers, roughly 110 kilometers from Petropavlovsk-Kamchatsky. The United States Geological Survey's moment magnitude calculation placed the event between 8.7 and 8.8. The International Seismological Center's independent calculation arrived at 8.7. This was, by either figure, the largest earthquake to strike anywhere on the planet since the 2011 Tohoku earthquake off Japan, and it ranks among the 10 largest earthquakes ever recorded by modern seismic instrumentation, a record that extends back to the early 20th century. The rupture itself was not instantaneous in the way a smaller earthquake's energy release can feel instantaneous. Seismic models built from the Geoscope Global Monitoring Network show energy release continuing for more than 180 seconds. The United States Geological Survey's finite fault model places the duration closer to 270 seconds, 4.5 minutes. A separate research team's analysis arrived at approximately 220 seconds. Averaged across these independent modeling approaches, the rupture itself lasted somewhere between 3 and 4.5 minutes, an extraordinary span of time for the ground to be actively breaking. The finite fault model indicated slip across a fault segment measuring approximately 600 kilometers long by 140 kilometers wide, an area of the seafloor roughly the size of Croatia, moving against itself in a single connected event. This earthquake did not arrive without warning, in the sense that seismologists understand warning. 10 days before the main shock, on the 20th of July 2025, a magnitude 7.4 earthquake struck nearby on the same subduction interface, a foreshock large enough that under ordinary circumstances it would itself have been the lead story of the week. In the 10 days between that magnitude 7.4 foreshock and the magnitude 8.8 main shock, the region produced 50 separate earthquakes of magnitude 5.0 or greater, including 3 separate magnitude 6.6 events. A research team from Temblor, working with seismologists from Tohoku University and Saisese, later compared this foreshock sequence to similar magnitude 7 to 7, 5 events in the Japan and Kuril trenches, and found that the Kamchatka foreshock sequence produced roughly 10 times the number of subsequent earthquakes within 10 days compared to typical sequences of similar size. Only one other modern sequence showed a comparably abnormal foreshock pattern, the 2-day foreshock sequence that preceded the 2011 Tohoku earthquake in Japan, which produced roughly 5 times the typical aftershock abundance. The researchers were careful to note that the vast majority of magnitude 7.0 plus earthquakes around the world do not precede an even larger event, and that this pattern alone could not have been used to predict the exact timing or scale of what followed. But after the fact, the data showed that the 10 days preceding the Kamchatka main shock carried a statistical signature that, in hindsight, marked the fault as unusually stressed. In the first hours after the magnitude 8.8 rupture, the United States Geological Survey logged 24 aftershocks above magnitude 5, including a magnitude 6.9 event and a magnitude 6.3 event, both within the first several hours. The aftershock sequence did not taper quickly. A magnitude 6.8 aftershock struck on August 3rd. A magnitude 7.4 aftershock, large enough to qualify as a major earthquake in its own right anywhere else on Earth, struck on September 13th, 46 days after the main shock. 5 days after that, on September 18th, a magnitude 7.8 aftershock struck, the largest aftershock in the entire sequence, nearly 2 full months after the original rupture. By the time researchers had finished cataloging the sequence through that period, more than 3,770 individual aftershocks above magnitude 4.0 had been recorded, 26 of them above magnitude 6. We want to pause on that September 18th figure specifically, because it matters for understanding what is happening this week. A magnitude 7.8 aftershock arriving 7 weeks after the original main shock is not a minor footnote. It is, on its own, large enough to have generated international headlines had it occurred as a standalone event anywhere else in the world. The fact that it occurred as an aftershock, 50 days into the sequence, illustrates something important about megathrust earthquakes of this scale. The timeline over which the surrounding crust continues to redistribute stress and produce significant seismic events is measured in months, not days, and in some documented cases, in years. The tsunami generated by the original main shock crossed the entire Pacific basin. The Pacific Tsunami Warning Center issued a tsunami warning for Hawaii and the Western Aleutian Islands, recommending evacuation, and issued tsunami advisories for Guam, American Samoa, and the Eastern Aleutians. Wave heights exceeding 1 meter were measured in Hawaii and in Northern California. Near the source, in Kamchatka itself, measured tsunami run-up reached 33.1 meters, more than 109 feet, in localized areas where coastal geometry concentrated the wave's energy. Despite the scale of the earthquake and the tsunami it produced, official figures attribute only 1 indirect death and 25 injuries, 21 of them indirect, to the entire event, a remarkably low casualty count for an earthquake of this magnitude, attributable to a combination of advanced tsunami warning systems, a relatively sparse coastal population in the immediate impact zone, and building codes in Petropavlovsk-Kamchatsky designed with seismic risk in mind. The agencies tracking this sequence operate on overlapping but distinct mandates, and understanding what each one actually does helps explain why the same earthquake can generate slightly different numbers depending on which source is reporting it. The United States Geological Survey operates the National Earthquake Information Center, headquartered in Golden, Colorado, which monitors seismic activity worldwide using a global network of seismometers, satellite communication links, and automated processing systems capable of issuing a preliminary magnitude and location within 2 minutes of any earthquake above magnitude 4.5 occurring anywhere on Earth. For events near coastlines, the USGS system also runs finite fault modeling, which attempts to reconstruct not just a single point of origin, but the actual geometry of the fault rupture, how far it extended, in which direction, and how much displacement occurred along its length. This is the modeling that produced the 600 kilometer by 140 kilometer slip estimate for the 2025 main shock, and it is also the modeling that allows the agency to issue its pager alerts. The automated casualty and economic loss estimates assigned a color code from green through red within roughly 30 minutes of a significant earthquake. The European Mediterranean Seismological Center, based in France, operates an independent monitoring network drawing on more than 65 seismological institutes across Europe and the Mediterranean basin, and despite its name, the agency tracks and reports on significant seismic activity globally, not solely within its namesake region. Its role in a sequence like this one is to provide independent cross-verification. When the USGS and the EMSC both report the same magnitude and depth for an event within minutes of each other, using entirely separate seismometer networks and separate calculation methodologies, that agreement is itself meaningful information. It means the reading is not an artifact of any single network's calibration or geographic blind spots. The German Research Center for Geosciences, GFZ, headquartered in Potsdam, operates the GeoFon Global Seismic Network and frequently serves as one of the fastest agencies to report a preliminary reading on any earthquake worldwide, often beating both the USGS and EMSC to an initial public alert by several minutes, though its early figures are subject to the same revision process as any other agency's preliminary data. The Pacific Tsunami Warning Center, operated by the United States National Oceanic and Atmospheric Administration out of Honolulu, Hawaii, holds a specific and narrow mandate, determining whether a given earthquake has displaced enough seafloor in the right geometry to generate a tsunami capable of threatening Pacific coastlines. This determination happens within minutes of any qualifying earthquake and is based on a combination of the earthquake's location, depth, magnitude, and fault mechanism, the direction and type of motion along the rupture. A shallow earthquake on a thrust fault, where one plate rides up over another, is far more likely to displace water vertically and generate a tsunami than a deep earthquake, or one involving primarily horizontal motion. For the magnitude 8 mainshock in 2025, the shallow depth and reverse thrust mechanism combined to produce a Pacific-wide tsunami threat within the center's first assessment window. For the June 19th and June 20th events, the center's assessment concluded no such threat existed, a determination made not because the magnitudes were too low in isolation, but because the specific combination of depth, location, and fault mechanism did not meet the threshold for significant vertical seafloor displacement. Finally, the Kamchatka branch of the Geophysical Survey of the Russian Academy of Sciences maintains the regional ground truth network closest to the source, with seismometers and GPS monitoring stations positioned directly on the peninsula and at seafloor locations where logistically possible. This regional network provides the most geographically precise data available for events in this specific subduction zone, though its publicly released figures move through Russian state channels on a different timeline than the rapid public alerts issued by USGS, EMSC, and GFZ. Each of these agencies, operating independently, with different equipment, different calculation methods, and different institutional mandates, arrived at substantially the same picture for the events of June 19th and June 20th. Real, measurable, shallow seismicity along a known and currently active fault system with magnitudes in the range that produces local shaking but, on their own, falls well short of generating a transoceanic hazard. The agreement across independent sources is itself part of the record. Seismologists have a formal name for the pattern that governs how aftershock sequences behave over time, and it predates modern seismology by more than a century. In 1894, Japanese seismologist Fusakichi Omori, studying the aftershocks of the 1891 Nobi earthquake, documented that the rate of aftershocks following a major earthquake decreases over time according to a predictable mathematical relationship. Aftershock frequency is highest immediately after the main shock and decreases roughly in proportion to the inverse of elapsed time. The formula has since been refined and is now known as the Omori-Utsu law, expressed as a rate of events per unit time that depends on a productivity factor tied to the main shock's magnitude, a short timescale constant, and a decay exponent, commonly labeled p, that is typically close to but not always exactly equal to 1. That decay exponent, p, is the number we referenced earlier in this report, and it is more useful to seismologists monitoring an active sequence than any single aftershock's magnitude in isolation, because it describes the overall health and trajectory of the entire sequence rather than any one event within it. A p-value close to 1 indicates a sequence decaying at a textbook standard rate, consistent with the kind of stress relaxation seen in most aftershock sequences worldwide. A p-value meaningfully below 1, sometimes written as a slow decay, indicates that aftershocks are persisting longer than the standard model would predict, often because the surrounding crust is releasing stress through a slower secondary mechanism called afterslip, in which the fault continues to creep, fault patches around the original rupture continuing to slip slowly over months or years rather than through additional sudden ruptures. Following the 2011 Tohoku earthquake in Japan, a megathrust event of similar scale and tectonic setting to the 2025 Kamchatka rupture, researchers analyzing post-seismic deformation found a decay pattern slower than the standard Omori prediction, a low p-value, consistent with significant ongoing afterslip continuing for years after the main shock. Omori's own original data, examined more than a century after he first published it, showed measurable aftershock activity from the 1891 Nobi earthquake persisting for 10 years following the main shock at diminishing but still detectable rates. The pattern these formulas describe is not a sequence that switches off. It is a sequence that fades, on a timeline that can be measured in years rather than days, with occasional larger aftershocks punctuating that overall decline in a way that is statistically expected even if any individual event cannot be predicted in advance. This is the context in which the events of June 19th and June 20th need to be read. 11 months after the original magnitude 8 rupture, this sequence is well within the time frame where standard aftershock models predict continuing seismicity, including occasional events in the magnitude 5 to 7 range. The specific diagnostic question seismologists are tracking is not whether these earthquakes are happening. It is whether the rate and magnitude distribution of events across the full 11 months since the main shock is consistent with a standard, well-behaved Omori-type decay, or whether the sequence is showing a slower decay pattern, the kind associated with significant ongoing afterslip, the kind that would suggest a longer overall window of elevated seismic hazard along this stretch of the trench than a textbook standard sequence would imply. As of this report, the publicly available aftershock catalog for the 2025 Kamchatka sequence shows exactly the kind of large, late-arriving events that a slow decay sequence would be expected to produce. The magnitude 7.8 aftershock on the 18th of September 2025 arrived 50 days after the main shock. The events of June 19th and the 20th of June 2026 arrived 325 and 326 days after the main shock, respectively, well outside what a textbook standard decay curve would predict as the active window for magnitude 6 plus events, though not outside what a slow decay, high afterslip sequence would predict. We want to be exact about what this does and does not mean. It does not mean another megathrust scale earthquake is imminent. It does mean that the working scientific assessment of how settled this fault actually is, 11 months on, remains an open and actively monitored question, not a closed one. The 2025 main shock did not confine its consequences to shaking and tsunami. In the days immediately following the rupture, the Institute of Volcanology and Seismology at the Russian Academy of Sciences Far Eastern Branch reported that 7 separate volcanoes across the Kamchatka Peninsula began erupting or showing significantly increased activity. The Institute's director described the event as the first instance in nearly 300 years of 7 volcanoes erupting simultaneously in the region, an occurrence rare enough that the director used the phrase, a parade of volcanic eruptions, to describe it to journalists. Klyuchevskoye, the tallest active volcano in the northern hemisphere at 4,750 meters, began erupting within hours of the main shock, sending ash plumes that would eventually reach 5 kilometers above sea level, and triggering a red aviation alert code from the Kamchatka Volcanic Eruption Response Team, the regional body known by the acronym KVERT that monitors volcanic hazards across the peninsula. Lava descending the volcano's slopes reached the Bogdanovich Glacier, accelerating ice melt and triggering mud flows that destroyed a dam built in 2023 to manage river flow in the area. More striking still was the eruption of Krasheninnikov, a volcano that, according to Olga Girina, head of KVERT, had not erupted in any historically confirmed instance in 600 years, beginning explosive activity within 4 days of the main shock. Scientists at the institute explicitly connected this eruption to the stress redistribution caused by the earthquake, an example of what geologists call earthquake-volcano interaction, in which the violent redistribution of crustal stress from a major seismic rupture can be sufficient to disturb a magma chamber that had otherwise remained stable for centuries. A peer-reviewed analysis published in the journal Science in February of 2026 examined the rupture using a combination of teleseismic data and satellite-based interferometric radar, finding that peak slip during the 2025 event exceeded the total slip deficit that had accumulated along this stretch of the fault since the 1952 earthquake, and explicitly cited the cascade of volcanic eruptions across multiple peaks as compelling evidence of the connection between megathrust rupture and regional volcanism. We mention this not because tonight's smaller earthquakes carry any documented connection to renewed volcanic activity, they do not, as of this report, but because it underscores the scale of what the 2025 rupture actually did to the regional crust. This was not an earthquake that broke one fault segment cleanly and then went quiet. It was an event large enough to alter pressure conditions in magma systems beneath multiple separate volcanic peaks across a region spanning hundreds of kilometers, a scale of crustal disturbance that takes considerably longer than 11 months to fully settle. As this report is filed, the Kamchatka branch of the Geophysical Survey continues to log seismicity along the trench in real time, and KVERT continues its independent daily monitoring of volcanic activity at Klyuchevskoy, Krasheninnikov, Sheveluch, and the other peaks that showed disturbance following the mainshock. The United States Geological Survey's aftershock forecast model for this sequence, last formally updated and made public in January of 2026, places the probability of an additional magnitude 6.0 or greater earthquake within the broader aftershock zone at levels that decline gradually over time but remain non-trivial across the coming months, consistent with the slow decay pattern we described earlier in this report. GPS monitoring stations positioned across the peninsula continue to record ongoing crustal deformation consistent with afterslip, the continued slow creep of fault patches surrounding the original rupture zone, a process that geodetic researchers studying the 2011 Tohoku earthquake found could continue measurably for years. What this means in practical terms for tonight's sequence is simple to state and considerably harder to resolve with certainty. The magnitude 6.6, 6, 4.9, and 5.8 earthquakes of June 19th and June 20th sit comfortably within the range of activity that scientists studying this fault consider possible and even expected at this stage of the sequence. They do not, on the data currently available, indicate an acceleration toward another rupture of the scale seen in 2025. But the working scientific position, stated plainly by researchers studying subduction zone aftershock behavior, is that an 11-month-old megathrust aftershock sequence on a fault this large remains an active, monitored hazard zone, not a closed case. That number will matter again later in this report, when we turn to what the historical written record says about how long sequences along this exact stretch of coastline have run in the past. To understand why this particular stretch of seafloor produces earthquakes of this frequency and scale, it helps to understand the specific tectonic machinery at work. The Kuril-Kamchatka Trench marks the boundary where the Pacific Plate, one of the largest of Earth's tectonic plates, is subducting, sliding underneath the Okhotsk Plate, a smaller plate that in turn sits at the edge of the larger Eurasian plate system. This is not a gentle, frictionless process. The two plates are in constant contact along an interface that extends from the surface down to depths of many tens of kilometers, and friction along that interface locks the plates together at most points, even as the underlying mantle convection continues to drive the Pacific Plate northwestward at roughly 80 millimeters per year, among the fastest convergence rates of any subduction zone on the planet. That locking is the entire mechanism behind megathrust earthquakes. Stress accumulates at the locked interface for years, decades, or centuries, as the plates continue trying to move past each other while friction holds the interface in place. Eventually, the accumulated stress exceeds the frictional strength holding the fault locked, and the interface ruptures suddenly, releasing in seconds or minutes the strain energy that had been building for a far longer period. The portion of the fault that ruptures, and how completely it ruptures, determines the magnitude of the resulting earthquake. A research team's published analysis of the 2025 rupture found that peak slip in the event, the actual distance the seafloor moved relative to itself during the earthquake, reached as much as 14 meters in the area offshore southern Kamchatka and Paramushir Island, and that this peak slip exceeded the total slip deficit, the cumulative backlog of unreleased motion that had built up along this stretch of the interface since the previous great earthquake in 1952. This detail matters considerably for understanding the current sequence. If the 2025 earthquake released more accumulated stress than had built up since 1952, that suggests the rupture was unusually complete for this segment, in the sense that it did not merely catch up on 70 years of accumulated motion but somewhat overshot it. Overshoot of this kind can produce complex aftershock behavior because the surrounding fault segments that did not rupture, areas immediately adjacent to the main slip patch, can experience sudden increases in stress as a direct mechanical consequence of the main rupture redistributing force into them. This stress redistribution is a well-established phenomenon in earthquake science, sometimes modeled using a calculation called Coulomb stress transfer, which estimates how much closer to failure a nearby fault segment is pushed by a rupture on an adjacent segment. The magnitude 7.4 aftershock on September 13th and the magnitude 7.8 aftershock on September 18th, both occurring on segments adjacent to but distinct from the original rupture patch, are broadly consistent with this kind of triggered failure on stress-loaded neighboring fault segments. The Kuril-Kamchatka trench has hosted exactly this kind of sequential, segment-by-segment failure before across documented history. The northern section of this same subduction zone produced a magnitude 8.4 earthquake in 1923, rupturing a segment located approximately 150 kilometers north of the 2025 epicenter. In the time since 1990 alone, before accounting for the 2025 event and its aftershocks, this offshore region has recorded nearly 700 separate earthquakes above magnitude 5.0, a background rate of seismicity that places it among the most consistently active subduction interfaces tracked anywhere by international seismic networks. International researchers studying the 2025 rupture in detail, combining teleseismic recordings from global monitoring stations with regional shake map products and satellite-derived geodetic offsets, found that the rupture propagated unilaterally, in essentially one direction along the fault, rather than spreading outward symmetrically from a central point, a rupture geometry consistent with what had been observed in the 1952 event on the same general stretch of interface. This kind of detailed agreement between two megathrust earthquakes separated by 73 years, both rupturing in a similar direction along a similar segment of the same trench, is itself a form of historical pattern recognition, just one conducted with modern instruments rather than human memory. This is, in the most direct sense available to us, simply what this particular stretch of ocean floor does, continuously, on a timescale that spans not years but centuries, with the current 11-month-old aftershock sequence representing the latest visible chapter of a process that has been running, by the written and instrumental record alone, for at least 300 years. We will return to that 300-year figure before this report is finished, because the written historical record for this exact coastline extends back almost exactly that far, and what it shows about the recurrence pattern of major earthquakes along this trench is worth examining in detail. The human story behind these numbers deserves its own accounting, because the contrast between the scale of the 2025 earthquake and its relatively modest casualty toll is itself part of the record worth understanding before we move forward. Approximately 1,400 buildings in Petropavlovsk-Kamchatsky sustained some degree of damage in the mainshock, roughly half the city's entire housing stock, according to figures presented to Russian President Vladimir Putin by Kamchatka Territory Governor Vladimir Solodov in a meeting held in early September of 2025. Despite that scale of structural impact, Governor Solodov confirmed there were no fatalities directly attributable to the earthquake within the region, a result he and regional officials attributed to building reinforcement programs and updated construction standards adopted in the years prior to the event, specifically because the region's seismic risk was already well understood by local authorities. The injuries that did occur were described as occurring mainly among people leaving buildings in haste, rather than from structural collapse itself. A kindergarten in Petropavlovsk-Kamchatsky was damaged. A ceiling section at Yelizovo Airport's terminal building collapsed, injuring one person. In the immediate aftermath, regional emergency services reported a measurable increase in calls related to high blood pressure, irregular heartbeat, and epilepsy. A detail that speaks to the acute physiological stress response a major earthquake produces in a population, even where physical injury is minimal. The town of Severokurilsk, in the Kuril Islands at the southern end of the affected zone, fared considerably worse in relative terms. More than 90% of chimneys in the town were toppled by the shaking. The subsequent tsunami inundated the port, sweeping away a fish processing plant and pushing seawater as far as 200 meters inland in places. This was not the town's first encounter with a wave of this kind. Severokurilsk had been almost entirely destroyed by the tsunami generated by the 1952 earthquake, after which officials relocated the bulk of the town to higher ground, leaving only the port facilities in the low-lying area nearest the water. That 2025 decision, made by an earlier generation of planners responding to an earlier disaster on this same coastline, is the reason the 2025 tsunami damaged a port rather than a residential center. The earthquake also measurably altered the physical geography of the peninsula itself. Danila Chebrov, director of the Kamchatka branch of the Unified Geophysical Service of the Russian Academy of Sciences, told Russian state media that GPS measurements taken after the main shock showed the area around Petropavlovsk-Kamchatsky had shifted horizontally by approximately 50 centimeters, nearly 20 inches, and that the peninsula had also decreased slightly in elevation. Chebrov noted that no serious consequences were expected from this shift, but the measurement itself illustrates something worth sitting with. An earthquake large enough to physically relocate a city's GPS coordinates and lower the land it sits on, an earthquake whose effects on the surrounding crust did not end the moment the shaking stopped. We raise the elevation and displacement data specifically because it bears on the question we will return to in the ancient records section of tonight's report. Across multiple independent traditions, separated by geography, language, and centuries, a specific and recurring claim appears regarding what happens to a coastline after the ground beneath it has been broken open in this way. Not merely that it shakes, but that something about its fundamental relationship to the sea changes afterward, that the boundary between land and ocean is itself renegotiated by events of this scale. We are not yet prepared to say what to make of that claim. We are noting that the instrumental data from this exact location, gathered by a Russian state geophysical agency using GPS, independently documents exactly the kind of permanent physical alteration those older traditions describe in their own language, without any access to satellites, benchmarks, or the mathematics of plate tectonics. Hold that thought. We will need it later. There is also a detail specific to Kamchatka's geography worth mentioning briefly, because it speaks to how thoroughly this region's population has organized its daily life around the reality of living atop one of the most active tectonic boundaries on Earth. The peninsula's brown bear population is large enough and sufficiently habituated to proximity with human settlements that Petropavlovsk-Kamchatsky maintains organized night patrols specifically to keep bears from wandering into residential areas, an ordinary fact of life in a region where the same geological forces that produce devastating earthquakes also produce the volcanic soil and salmon-rich rivers that sustain one of the densest brown bear populations on the planet. We mention this not as a curiosity, but as a way of underscoring a theme that will recur throughout tonight's report. The people who have lived along this coastline longest have always understood it as a place where extraordinary danger and extraordinary abundance share the same ground, often within the same square mile. The Kuril-Kamchatka Trench does not operate in isolation. It is one segment of a much larger structure that seismologists and geographers refer to as the Pacific Ring of Fire, a roughly 40,000 kilometer chain of subduction zones, fault systems, and volcanic arcs that traces nearly the entire circumference of the Pacific Ocean basin, from the southern tip of South America, up the western coast of North America, across the Aleutian Islands, down through Kamchatka and the Kuril Islands, through Japan, the Philippines, Indonesia, and around to New Zealand. Roughly 90% of the world's earthquakes and the vast majority of its active volcanoes occur somewhere along this ring, a consequence of the fact that nearly the entire Pacific Plate, one of the largest and most rapidly moving tectonic plates on the planet, is actively subducting beneath nearly every plate that borders it. This matters for tonight's report because the Kamchatka sequence is not occurring in a vacuum. Earlier this year, in April of 2026, a magnitude 7.4 to 7.5 earthquake struck the Tohoku region of Japan, several hundred kilometers south of Kamchatka, along the same general arc, preceded by its own foreshock sequence beginning in November of 2025 that included 5 separate events above magnitude 6. That earthquake, occurring on the Japan Trench, a related but distinct segment of the same broader subduction system that includes the Kuril-Kamchatka Trench to its north, caused measurable but limited damage, with around 233 structures affected and 10 injuries reported, no fatalities. We mention it specifically because it illustrates a pattern seismologists watching the broader Pacific Rim have long understood. Large earthquakes on one segment of a subduction system do not occur in strict isolation from the segments around them, even when no direct triggering relationship can be proven for any individual pair of events. The Pacific Plate's overall motion places stress on the entire chain of subduction interfaces simultaneously, and while a rupture on one segment does not mechanically guarantee a rupture on a neighboring segment, the broader system as a whole remains in a continuous state of stress, accumulation, and release across thousands of kilometers. Closer to the calendar of this specific report, a magnitude 7.8 earthquake struck off the southern coast of Mindanao in the Philippines on June 8th of this year, 11 days before the Kamchatka events we are reporting on tonight. That earthquake, also along the broader Pacific Ring of Fire, though on a structurally distinct fault system from the Kuril-Kamchatka Trench, produced its own significant aftershock activity and prompted extensive emergency response across the Sarangani and Davao Occidental provinces. We raise it not to suggest any direct mechanical connection between the Mindanao sequence and the Kamchatka sequence. Current seismological understanding does not support drawing that kind of connection between earthquakes on unrelated fault systems separated by this distance, but to place tonight's Kamchatka data within the broader context of a Pacific basin that has produced an unusually dense cluster of major seismic events across this calendar year. Seismologists are careful, and we want to be equally careful here to distinguish between two very different claims. The first claim, that earthquakes across the Pacific Ring of Fire are mechanically connected in a chain reaction, where one event directly causes another thousands of kilometers away, is not supported by current science, except in rare, specific, well-documented cases of nearby fault segments triggering each other through measurable stress transfer, the kind of triggering we discussed earlier regarding the September 2025 aftershocks on segments adjacent to the original Kamchatka rupture. The second claim, that the Pacific Plate, as a whole, exists in a continuous, ongoing state of stress that produces a generally elevated background rate of major seismicity across the entire ring during certain periods, is well supported by the historical and instrumental record, even though predicting precisely where or when any individual rupture will occur remains beyond current scientific capability. Tonight's report concerns itself with the first kind of claim only insofar as it applies to the documented, measurable relationship between the 2025 Kamchatka mainshock and its own aftershock sequence. We are not asserting, and the data does not support asserting, any direct causal link between Kamchatka and the other Pacific earthquakes mentioned here. We mention them because understanding the broader pattern of activity across the Ring of Fire this year provides useful context for how unusually active the overall system has been, even as each individual sequence is best understood and monitored on its own terms. This is also, as it happens, exactly the kind of pattern, the recognition that the wider ocean and the land around it behave as a single interconnected system rather than a collection of unrelated local events, that several of the oldest recorded human traditions concerning this ocean basin appear to have grasped, centuries before any instrument existed capable of measuring a tectonic plate's motion. We are not there yet. We will get there. For now, we return to the specific data from this week, because there is one more piece of the instrumental record that deserves full attention before we leave the briefing behind. What happens next along this stretch of the Kuril-Kamchatka trench is, by the nature of earthquake science, not something any agency can predict with precision. But the agencies monitoring this sequence have been explicit about what they are watching for, and naming those specific indicators gives a clearer picture of how seismic hazard assessment actually functions in an active sequence like this one than any single forecast. Number CUD, the United States Geological Survey's aftershock forecasting model, the same modeling framework used to generate the widely cited estimate following the main shock that further aftershocks up to magnitude 7. 5 remain possible, continues to be updated as new data arrives, and the agency maintains a standing aftershock advisory specifically for sequences of this scale, recalculating probability windows as the sequence ages. The core question that model is built to answer is not whether more earthquakes will occur in a sequence this large. More earthquakes are essentially guaranteed for an extended period, but rather how the probability of a damaging event, magnitude 6, 0 or higher, within a given time window changes as the sequence matures. 11 months in, that probability has declined substantially from where it stood in the days immediately following the main shock, but it has not declined to 0, and the events of June 19th and 20th are consistent with a still elevated, still monitored probability window rather than an anomaly outside it. The Kamchatkan branch of the Geophysical Survey maintains continuous broadband seismic monitoring across the peninsula, specifically to catch any change in the character of seismicity along the trench, not just its frequency. Seismologists watching a sequence like this pay close attention to several specific signals beyond simple event count, whether earthquake depths are migrating toward the surface or deeper into the crust, which can indicate changing stress conditions at different points along the subduction interface, whether the spatial distribution of events is expanding into new sections of the fault that had not previously shown activity, and whether the ratio of larger to smaller earthquakes, a statistical relationship known as the Gutenberg-Richter distribution, remains consistent with the established pattern for this fault or begins to shift. KVERT continues separate daily monitoring of the volcanic systems disturbed by the original main shock, specifically Klyuchevskoy, Krasheninnikov, and Shiveluch, watching for any indication that continued seismic activity along the trench is further altering pressure conditions in the magma systems beneath these peaks. As of this report, KVERT's most recent public advisories show continuing background activity at multiple monitored volcanoes, but no escalation directly attributable to the June 19th or June 20th. Seismicity specifically. The Pacific Tsunami Warning Center maintains its standing protocol of evaluating every earthquake above a minimum magnitude threshold occurring anywhere along the Pacific Basin for tsunami potential within minutes of detection, a protocol that activated and cleared without incident for both June 19th and June 20th, and that will activate again automatically for any subsequent earthquake meeting the threshold criteria, regardless of whether that earthquake originates from the Kamchatka sequence specifically or from an entirely separate fault system elsewhere along the Ring of Fire. For residents and observers specifically watching this sequence, the practical guidance from regional authorities has remained consistent since the immediate aftermath of the 2025 main shock, continued vigilance regarding tsunami evacuation, routes in coastal areas, ongoing structural inspection of buildings that sustained damage in the original event, and awareness that aftershock activity, including occasional events large enough to be felt strongly and reported internationally, remains an expected feature of life along this coastline for the foreseeable future. This is not language designed to alarm. It is the standard operating guidance for any population living atop an active aftershock zone following a megathrust earthquake, the same guidance that was given to residents of Tohoku, Japan, following the 2011 earthquake there, and the same guidance, as we are about to examine, that this exact stretch of Kamchatka coastline has received from its own residents and visitors, in one form or another, following each of the great earthquakes that struck before instruments existed to measure them. 4 agencies, 3 nations worth of monitoring infrastructure, and more than a century of accumulated seismic theory currently stand watch over this single stretch of subduction interface. That is the modern apparatus. What existed before it, on this same coastline, is where we turn next. Before we leave the instrumental record and turn to history, it is worth taking stock of everything tonight's data has actually established, because the historical section that follows will measure itself directly against these numbers. We know that a magnitude 6.6 earthquake paired with a magnitude 6 event 1 minute prior and a magnitude 4.9 event 13 minutes after struck the Kuril Kamchatka trench at 6:52 UTC on the 19th of June, 2026, confirmed independently by the United States Geological Survey, the European Mediterranean Seismological Center, the German Research Center for Geosciences, and Russia's own Kamchatkan branch of the Geophysical Survey. We know a fourth event, magnitude 5.8, struck the same general area less than 30 hours later on the afternoon of June 20th. We know all four events occurred within the active aftershock zone of the magnitude 8.8 to 8.7 megathrust earthquake that ruptured this same interface on the 29th of July, 2025, an event that ranks among the 10 largest ever recorded by modern instruments, that triggered a Pacific-wide tsunami that disturbed 7 separate volcanic systems across the Kamchatka Peninsula, including one, Krasheninnikov, that had not erupted in any historically confirmed instance in 600 years, and that physically shifted the ground beneath Petropavlovsk-Kamchatsky by nearly 20 inches, while measurably lowering the peninsula's elevation. We know that the mathematics governing how aftershock sequences decay over time, formalized more than a century ago and refined continuously since, predicts exactly the kind of continuing, gradually diminishing but still significant seismicity that this sequence has shown for 11 months running, with large, late-arriving events, the September 2025 magnitude 7.8 aftershock, the June 2026 events we are reporting tonight, falling within the range that a slow decay sequence, the kind associated with substantial ongoing afterslip, would be expected to produce. That number will matter again in a moment. We know that this entire stretch of the Kuril-Kamchatka trench has produced exactly this pattern of major rupture followed by extended, sometimes years-long aftershock activity at least twice before in the documented historical record in 1952, and further back in 1737, both involving the same general segment of subduction interface now hosting the current sequence. What the instrumental record cannot tell us, because instruments capable of measuring any of this did not exist before the 20th century, is what this exact pattern looked like to the people who lived through it the first few times it happened. The written historical record for this coastline, assembled from ship logs, missionary accounts, and early Russian administrative records, extends back nearly 300 years to the era of the 1737 earthquake itself, and gives us our first opportunity to compare tonight's instrumental data against documented human experience of the same fault behaving the same way, generations before anyone had a name for an aftershock sequence or an Omori decay curve. There is a name in the record we are about to enter that matches this exact stretch of coastline with unusual precision, and we are not there yet. We want you to keep both things in mind as we proceed. The slow decay aftershock signature this fault has shown for 11 months, and the simple fact that 2 earlier generations of people living on this same peninsula independently recorded watching this same fault behave the same way, long before any of them had a word for plate tectonics. By the time we reach the ancient record section of tonight's report, we will show you exactly how far back that pattern of recognition actually extends, into traditions that predate the written Kamchatkan record by well over 1,000 years, on the opposite side of this same ocean. We turn to the historical record now. The written historical record for this exact stretch of coastline begins, for practical purposes, on the 17th of October, 1737, local time, when a megathrust earthquake estimated at magnitude 9 to as high as 9.3 ruptured the same general segment of the Kuril-Kamchatka trench now hosting the current sequence. The account that survives comes from Stepan Krasheninnikov, a Russian explorer and naturalist who arrived in Kamchatka only a few years after the event and compiled detailed interviews with surviving residents, both Russian settlers and indigenous Itel men and Koryak communities, publishing his findings in 1755 under the title Description of Kamchatka land. According to Krasheninikov's account, the shaking lasted approximately 15 minutes, an extraordinary duration that closely echoes the multi-minute rupture duration modern instruments measured for the 2025 earthquake on this same fault. Wooden and skin dwellings belonging to native communities were destroyed across the region. The Bolsheviks Cossacks stationed in the Kuril Islands at the time later told Krasheninnikov that at the first violent shock, they fled with island residents to higher ground and abandoned all of their possessions, which were entirely lost to the tsunami that followed. Krasheninnikov documented 3 separate destructive waves striking the coast, with run-up heights along the eastern Kamchatka shoreline reaching as high as 30 fathoms in places, roughly 55 meters, among the most extreme tsunami run-up figures recorded anywhere on Earth before the era of modern instrumentation. Specific accounts preserved through Krasheninnikov's interviews record at least 3 confirmed drownings near Avacha Cove, 2 women and 1 man, whose dwelling was carried off by the flood as they attempted to escape it. What concerns us most directly tonight is what Krasheninnikov's account says happened after the main shock. He recorded that aftershocks continued to be felt even as the tsunami waves were actively striking the coast, and that the sequence of felt aftershocks did not subside until the following spring, in 1738, a duration of approximately 5 months. Within that aftershock window, a separate large event struck on the 17th of December 1737, 2 months after the main shock, estimated at magnitude 7.5 and large enough to trigger its own secondary tsunami along the coast. We want to be precise about the parallel here because precision is the only thing that makes a historical comparison meaningful rather than merely poetic. A magnitude 7.5 aftershock, arriving 2 months after a megathrust main shock, documented by a trained naturalist conducting direct interviews with surviving witnesses in 1737, is structurally the same kind of event as the magnitude 7.8 aftershock that struck this same general fault segment on the 18th of September 2025, 50 days after that main shock. 2 different centuries, 2 different instruments, one measured by a Russian explorer's interview notes and the other by a global network of digital seismometers, recording what appears to be the same underlying behavior of the same stretch of subducting crust. When the German naturalist Georg Wilhelm Steller visited the same region in 1740, 3 years after the earthquake, he documented finding the bones of marine mammals and driftwood lying well above the existing tide line, physical evidence of just how far inland the tsunami's waters had reached, and a permanent alteration to the coastal landscape that remained visible years after the event itself. Modern geological research, examining buried erosional scarps and tsunami deposits along the Kamchatka coast, has identified evidence of coastal subsidence, the land itself sinking relative to sea level, associated with this same category of unusually wide subduction zone rupture, occurring only a handful of times across the last 4,000 years of geological record, with the most recent confirmed instance prior to 1737 occurring roughly 1,200 years earlier. That number will matter again before this report is finished. The second great earthquake in the written record for this coastline struck on the 4th of November 1952 at a magnitude now generally accepted at 9.0, rupturing a segment of the trench that overlapped substantially with the same general area later involved in both the 1737 and 2025 events. The town of Severokurilsk, which we mentioned earlier in tonight's report in connection with the 2025 tsunami damage to its port facilities, was almost entirely destroyed by the 1952 tsunami, with waves reported between 15 and 18 meters, striking the settlement directly, arriving as 3 successive surges rather than a single wave. Most residents recognized the initial withdrawal of the sea, the characteristic warning sign of an approaching tsunami, and fled to higher ground before the first wave struck, but a significant number returned to the town between waves, believing the danger had passed, only to be caught by the second and third surges. Official figures place the death toll from the 1,952 disaster between roughly 2,300 and as high as 14,000 people, depending on the source consulted, with the lower, more conservative figure of 2,336 most commonly cited in modern seismological literature, a discrepancy researchers attribute in part to the Soviet government's decision to suppress detailed public reporting on the disaster for decades afterward, treating the true scale of the destruction as a closely held state matter rather than a publicly documented catastrophe. The tsunami crossed the entire Pacific basin within 9 hours, reaching Hawaii, where it destroyed boats, downed telephone lines, demolished piers, and scoured beaches. Though it caused no recorded human fatalities there, only the deaths of 6 cows. Severokurilsk was rebuilt by deliberate decision of post-war Soviet planners on higher ground further inland, a direct and permanent change to the human geography of the coastline, made specifically in response to what the 1952 earthquake had demonstrated about the vulnerability of the coastline. Original town site. It is that exact relocation decision, made by a generation of planners responding to the 1952 disaster, that explains why the 2025 tsunami damaged only a port and a fish processing facility in Severokurilsk rather than the town's residential core, 73 years and one entire human lifetime after the decision that protected it was made. The decisions made by survivors of one great earthquake along this coastline directly shaped how much damage a different great earthquake, 73 years later, was capable of inflicting on their descendants. We have, across these 2 documented events alone, separated by 2 centuries and recorded using entirely different methods, by a Russian naturalist's interview notes in one case, and by 20th century seismographs in the other, the same essential signature now showing up a 3rd time in this week's instrumental data, a megathrust rupture along this trench, followed by an extended aftershock sequence lasting months, punctuated by individual aftershocks large enough to register as significant earthquakes in their own right, with the entire sequence leaving a permanent mark on the physical landscape and the human settlements built upon it. That pattern is now on the record 3 separate times for this exact stretch of coastline, recorded by 3 different methods, across nearly 300 years. We will return to this coordinate, the stretch of seafloor between Petropavlovsk-Kamchatsky and the Kuril Islands, before the end of tonight's report, because there is a name for this exact location that appears in a tradition far older than Krasheninikov's notebooks. There is a 4th instance worth placing alongside these 2, more recent and instrumentally precise than either, that demonstrates this same pattern operating on a still shorter and more clearly documented timeline. On the 21st of April, 2006, a magnitude 7.6 earthquake struck the Olutor region of Kamchatka's Koryak Autonomous Okrug, a few hundred kilometers north of the area affected by tonight's sequence, destroying the villages of Apuka, Kailino, and Vivenka and injuring 40 people. Field surveys following the earthquake identified a surface rupture zone 140 kilometers long. The aftershock sequence that followed produced 2 separate magnitude 6 earthquakes, one on April 29th, 8 days after the main shock, and a second on May 22nd, a full month later. Then, on the 13th of January 2007, nearly 9 months after the original April rupture, a separate great earthquake measuring magnitude 8, one struck within the same aftershock zone established by the 2006 event. Researchers studying the pairing identified it as one of the largest documented earthquake doublets, 2 major earthquakes linked by measurable stress transfer, ever recorded at a subduction zone, evidence that the 2006 rupture had redistributed stress in a way that helped trigger the second, considerably larger earthquake 9 months later. We mention this 4th case specifically because it demonstrates, using fully modern instrumentation with none of the interpretive uncertainty that necessarily attaches to an 18th century witness account, that this exact subduction system is capable of producing significant triggered earthquakes on a timeline stretching to 9 months and beyond, a timeline that places tonight's 11-month-old sequence squarely within the range this fault has already demonstrated twice within the last 20 years. The pattern in the modern record is clear, but we do not stop at the modern record. There is an older layer, tablets, manuscripts, oral traditions, documented predictions, that logged events matching this signature long before our instruments existed to confirm them. That layer is what comes next. There is a question we planted earlier in this report, in the briefing section, Concerning a specific diagnostic threshold seismologists use to measure whether an aftershock sequence is decaying at a standard rate or persisting longer than expected. We answered that question directly. The decay exponent known as P and the 11-month-old Kamchatka sequence's apparent consistency with a slow decay pattern rather than a textbook standard one. We raise that answer again here, at the opening of this section, because the three traditions we are about to examine each independently arrived at a version of the same underlying recognition, centuries or millennia before Fusakichi Omori ever wrote down a formula, that an earthquake is not a single event but the visible beginning of an extended process, one that continues to unfold, in stages, over a span of time considerably longer than the initial shaking itself. We begin directly across the Pacific, from Kamchatka, on the islands of Japan, with a tradition that developed independently along the same broader seismic belt that includes the Kuril Kamchatka Trench, the Japan Trench, and the wider Ring of Fire system we discussed in the briefing. Japanese folklore attributes earthquakes to the movement of a giant catfish, known as Namazu, said to live in the mud and water beneath the Japanese archipelago. The tradition, as documented by historians and folklorists studying its development, appears to have evolved gradually between the 15th and 18th centuries, with earlier versions of the same basic concept, attributing earthquakes to a giant dragon or serpent rather than a catfish specifically, a shift folklorists attribute to the existing cultural association
and these
between water-dwelling
have
creatures and the unpredictable, destructive power of both earthquakes and the tsunamis that often follow.
The end is not.
According to the fully developed version of the tradition, Namazu is restrained beneath a sacred capstone called the Kaname-ishi, placed and maintained by the thunder god Takemikazuchi specifically to keep the catfish pinned in place. The mythology holds that earthquakes occur when Takemikazuchi's attention lapses, whether because the god is away attending a periodic council of other deities, as one version of the story holds, or because a designated guardian deity assigned to watch the catfish in Takemikazuchi's absence falls asleep at the task, as a related variant explains. In either telling, the mechanism is consistent. Earthquakes happen specifically when vigilant restraint over the catfish's movement is interrupted, and the resulting shaking is described not as a single, instantaneous convulsion, but as the catfish thrashing, an ongoing, repeated motion rather than one sharp jolt. The tradition entered its most extensively documented phase following the Ansei Edo earthquake of 1855, a magnitude 7.0 event that struck the city now known as Tokyo and killed an estimated 7,000 people. In the immediate aftermath, an entirely new genre of woodblock print called Namazu-e, or catfish pictures, appeared and circulated widely throughout the city within days of the disaster. Historians studying these prints, most notably Gregory Smits in his detailed academic analysis of the Ansei Edo print tradition, have cataloged and analyzed hundreds of surviving examples, finding that the prints served multiple overlapping cultural functions simultaneously. Protective talismans that buyers believed could ward off future earthquakes when affixed to a home's ceiling, social commentary on the redistribution of wealth and destruction across different classes of Edo society, and a shared cultural vocabulary that allowed a traumatized population to process and discuss a catastrophic, poorly understood natural event using a shared set of familiar symbols and characters rather than scientific language that did not yet exist. One specific and recurring motif across these prints depicts Namazu as an agent of what the tradition calls yonaoshi, or world rectification, the idea that the catfish's destructive thrashing, while devastating, ultimately served a redistributive social function, an idea documented across multiple surviving prints and discussed at length in academic treatments of the genre. What concerns us specifically for tonight's report is a detail embedded in the historical record surrounding the origin of the Namazu belief itself, separate from the later 1855 prints. According to the version of the tradition's origin most widely cited by folklorists, a Japanese eel fisherman's account of observing unusual catfish behavior immediately preceding a specific historical earthquake is frequently identified as a contributing source. For the broader
What's
cultural
happening?
association between catfish and seismic activity, an account that predates the systematic study of animal behavior as a potential earthquake precursor by Japanese seismologists in the 20th century by a considerable margin. In the 1930s, Japanese researchers undertook formal scientific study of whether catfish behavior could serve as a measurable, predictive signal of impending seismic activity, building directly on the cultural intuition embedded in centuries of Namazu folklore, with one researcher reporting having observed catfish exhibiting unusual behavior patterns that correlated in his data with a notable number of subsequent earthquakes within a following window of several hours.
Increasing.
We want to be precise about the limits of this connection. Modern seismology has not validated catfish behavior as a reliable, generalizable earthquake precursor, and we are not asserting that it has. What we are noting is the documented historical fact that a culture living atop one of the most seismically active archipelagos on Earth developed, centuries before instrumental seismology existed, a structured cultural framework that treated the natural world around them, specifically the behavior of an aquatic creature, as a meaningful signal worth watching in relation to the ground's stability, and that this folk intuition later became the explicit subject of formal 20th century scientific inquiry rather than being dismissed outright as superstition unworthy of study. The structural detail in the Namazu tradition most relevant to tonight's Kamchatka sequence is this.
Will shake the
In
earth.
every version of the myth, the earthquake is never described as Namazu's single, isolated action. The catfish is consistently described as continuing to thrash, requiring continued restraint, implying an ongoing struggle between the catfish and its restrainer rather than a one-time event with a clean beginning and end. A tradition built around the idea that the ground's instability is a persistent condition requiring continuous vigilance and continuous restraint, rather than a single, discrete event that concludes the moment the visible shaking stops, describes, in its own cultural language, precisely the kind of extended, multi-month aftershock sequence that modern seismology measures using the Omoriutsu decay curve we explained earlier in this report. We move now to a tradition geographically distant from the Pacific Basin entirely, recorded in a different language, by a different culture, with no plausible historical contact between its authors and the people of ancient Japan or, as we will examine shortly, the Hopi mesas of the American Southwest. The Book of Isaiah,
The secrets of
part
the
of
ages
Hebrew
wait
prophetic
here
corpus,
for those who dare to read.
is generally dated by biblical scholars to a composite period spanning roughly the 8th through 6th centuries before the Common Era, with chapter 24 specifically falling within a section often referred to by scholars as the Isaiah Apocalypse, chapters 24 through 27, a passage whose precise dating remains debated among textual historians, but which most scholarly consensus places no later than the early post-exilic period.
They say that every story has an ending, but in the world of knowledge, the story never truly ends.
The relevant passage,
This text
Isaiah 24, verses 18 through
holds a
20,
secret.
describes a specific sequence of ground-based catastrophe using vivid, deliberately escalating language. The text describes the Earth's foundations shaking, then the Earth itself breaking apart, splitting open, and being violently shaken, and finally the Earth staggering and swaying like a drunken man or flimsy shelter in a storm, language that multiple standard English translations render with strikingly consistent imagery, despite differing word choices across translation traditions. We want to draw attention specifically to the structure of this passage rather than to any single word within it, because the structure is what matters for tonight's comparison. The text does not describe a single instantaneous event. It describes a sequence. First, the foundations shake, then the Earth breaks and splits, then the Earth staggers and sways, language that depicts an unfolding, multi-stage process rather than one discrete moment of shaking followed immediately by stillness. Biblical scholars examining this passage have noted that the broader context of chapters 24 through 27 pairs this earthquake imagery directly with imagery of burning, of
Seismic
fire
activity
consuming
is
the land,
increasing. A
appearing earlier in the
large-scale
same
volcanic
chapter.
eruption is imminent.
The two phenomena, ground motion and thermal or fire-related disturbance, are presented within the same continuous prophetic vision rather than as separate, sequential disasters. We are not asserting that the authors of Isaiah possessed any technical understanding of the relationship between megathrust earthquakes and the volcanic systems they can disturb. The relationship we documented at length earlier in this report regarding the 7 Kamchatka volcanoes that began erupting within days of the 2025 mainshock. Krasheninikov's eruption after 600 years of dormancy chief among them. We are noting, as a matter of textual observation available to any reader regardless of belief, that a text composed roughly 26 centuries ago pairs seismic and thermal earth disturbance within a single continuous vision of a compound natural catastrophe, a pairing that happens to match, in its basic structure, the documented geophysical relationship between megathrust rupture and triggered volcanism that modern seismologists and volcanologists now study as an established field of earthquake-volcano interaction. The progression described in verses 18 through 20 carries a specific temporal structure worth examining closely. The passage does not present its climax first. It builds toward it, describing terror and a trap and a snare as an initial condition, then the foundations shaking, then the earth breaking and splitting, then finally the staggering and falling that the text describes as final and irreversible.
The end is...
Read as a description of an unfolding physical process rather than purely as theological metaphor. The structure bears a specific resemblance to how a megathrust earthquake sequence actually unfolds in the geological record. An initial disturbance, escalating structural failure, and then an extended period of instability, staggering, in the text's own language, before any final settling. The Hebrew verb forms used across these verses, examined by scholars working directly with the original language rather than translation alone, consistently employ active, ongoing, repeated motion rather than a single completed action, grammatically reinforcing the sense of a sustained rather than momentary disturbance. We want to be exact about what we are and are not claiming here, in keeping with the analytical standard we hold to throughout this report. We are not claiming that Isaiah 24 constitutes a scientific prediction of the 2025 Kamchatka earthquake, the Kuril Kamchatka Trench, or any specific geographic location. The text contains no place name, no date, no measurement that could be matched to a specific modern coordinate. What we are observing, carefully, and without overstatement, is that a 26th century-old text, working entirely without access to seismographs, satellite geodesy, or the mathematics of plate tectonics, nonetheless arrived at a structural description of ground failure as an extended, multi-stage process rather than a single instant
seismic activity along the East Asian seaboard is within normal
with what
parameters.
The instrumental record now
Monitors
confirms
are
about how this exact category of earthquake, the megathrust subduction event,
Data
actually
stream
behaves over the
initiated.
11 months following its
14
initial
months
rupture.
sequence Junzai Jazide.
The language used is precise enough in its description of sequence and duration to be notable on those grounds alone, independent of any theological reading a given audience might bring to the text. The third tradition we examine tonight comes from the Hopi people of the high desert mesas of what is now northeastern Arizona, an oral tradition maintained continuously by Hopi clan elders for a documented minimum of 8 centuries of settlement in the region, with the oral tradition itself extending considerably further back than the archaeological record of physical settlement can independently confirm. The Hopi cosmological framework describes a sequence of 4 previous worlds, each of which concluded through a specific catastrophic transformation, with the current age understood as the 4th world, itself approaching a transition the tradition calls the Great Purification. This tradition differs from both Namazu and Isaiah 24 inches, an important respect worth naming directly. It has been actively documented and publicly transmitted by named, identifiable individuals within living historical memory, rather than reaching us solely through ancient text or centuries-old folklore compilation. Dan Kachongva, a Sun Clan leader from the Hopi village of Hotavia who lived to the age of 112 and died in 1972, gave extensively documented public testimony throughout the mid-20th century regarding the specific signs his tradition held would precede the Great Purification. Speaking in 1970, in testimony that has since been transcribed and preserved by researchers studying Hopi prophecy, Kachongva specifically named earthquakes and floods as causing great disasters among the signs the tradition instructed Hopi elders to watch for, alongside changes in season and weather patterns and the disappearance of wildlife. David Mononier, another elder from the same Third Mesa community, separately and independently emphasized earthquakes, floods, hailstorms, drought, and famine becoming a condition of daily life as the specific marker indicating the time of decision had arrived. A separate strand of the same broader tradition reached wider public documentation through an account given by a Hopi elder known as White Feather of the Bear Clan, who in 1958 provided a minister named David Young with what has since been referred to in researched accounts of Hopi prophecy as the 9 signs, a structured sequence of historical and natural developments the tradition held would mark the approach of the Fourth World's end. We note this account specifically because of its documented chain of transmission. A named Hopi elder speaking to a specific named individual in a specific recorded year, whose account was subsequently written down and has been cross-referenced by multiple researchers studying Hopi prophecy independently, giving this strand of the tradition an unusually well-documented provenance compared to oral traditions generally, where transmission details are frequently lost to history. Central to the broader Hopi prophetic framework is a specific physical artifact, a petroglyph panel carved into a sandstone boulder near Hotevia known as Prophecy Rock, which depicts 2 diverging paths available to humanity, one aligned with traditional land-based living and one aligned with technology and departure from natural law, with the prophecy holding that continued movement along the technological path leads inevitably toward the period of catastrophic purification, explicitly including earthquakes among the specific natural disturbances the tradition associates with that period. Hopi cosmology describes this purification not as a single, instantaneous event, but as a process, a gradually intensifying pattern of natural disturbance, with the previous 3 worlds each having concluded through a specific extended catastrophic process rather than a single sudden conclusion. A structural feature of the cosmology that researchers studying Hopi mythology have noted recurs consistently across the tradition's account of all 3 prior world endings. We want to be precise here, in the same register we have used throughout tonight's examination of every tradition under discussion. We are not asserting that the Hopi tradition predicted the specific magnitude 8 earthquake that struck Kamchatka in July of 2025, a location roughly 9,000 kilometers from the Hopi mesas, with no documented historical contact between Hopi tradition bearers and the indigenous or Russian populations of the Kamchatka Peninsula. What we are observing is that this tradition, maintained and transmitted by named, documented elders across the 20th century, independently arrived at a framework in which earthquakes function not as isolated, one-time events, but as part of an extended, escalating natural process unfolding across an extended period, a structural understanding of seismic activity as gradual and cumulative rather than instantaneous, that, once again, aligns with what the instrumental Omoriutsu decay data examined earlier in this report actually documents about how a real subduction zone aftershock sequence behaves across the 11 months following its initial rupture. We now have 3 traditions in front of us. A Japanese folk tradition describing earthquakes as the ongoing, repeated thrashing of a restrained creature rather than a single discrete event. A Hebrew prophetic text, composed 26 centuries ago, describing ground failure as an escalating multi-stage process rather than an instant. A documented 20th century Hopi oral tradition describing earthquakes as markers within an extended, gradually intensifying period of natural disturbance rather than isolated incidents. 3 cultures, on 3 different continents, working in 3 different languages, across a span of recorded transmissions stretching from roughly the 6th century before the Common Era through living testimony recorded in 1958 and 1970, independently arrived at the same basic structural insight that modern seismology did not formalize mathematically until Omori's 1894 publication, that an earthquake is not a single moment, but the visible opening of an extended process. It is worth comparing these 3 traditions directly against each other before we close this section, because the differences between them are as informative as the similarity that unites them. The Namazu tradition is the most geographically proximate to tonight's earthquakes, developed along the same broad seismic belt, and frames the ongoing nature of seismic disturbance through the image of restraint repeatedly lapsing, an earthquake as the temporary failure of a containing force rather than a self-contained event. Isaiah 24 is the oldest of the three traditions in terms of original composition, predating the others by well over 2,000 years in the case of the Hopi testimony and by several centuries in the case of Namazu's earliest folkloric origins, and frames the extended seismic process in the language of escalating structural collapse, building toward an irreversible final state. The Hopi tradition is unique among the three for the comparative clarity of its modern documentation, transmitted through named individuals whose specific testimony was recorded, dated, and preserved within living memory, and frames the extended seismic process explicitly as a marker within a larger pattern of accumulating natural disturbance, one sign among several rather than an isolated phenomenon. None of these three traditions shares a documented historical point of contact with either of the other two. The geographic distances involved, Japan to the eastern Mediterranean region where Isaiah was likely composed, and either of those locations to the high desert of northeastern Arizona, eliminate any plausible route of direct cultural transmission using the historical and archaeological evidence available to researchers. What we have, instead, is three independent human observational traditions, separated by language, geography, and centuries, that arrived at structurally convergent descriptions of how the ground behaves when it has been broken open by a major seismic event, not as a single, concluded incident, but as an extended condition requiring continued attention, continued vigilance, and an understanding that the visible shaking is the beginning of a process rather than its entirety. This is, in the most literal and least mystical sense available to us, simply a description of an aftershock sequence arrived at independently by three separate human cultures, using nothing but sustained observation across generations and the cultural and religious frameworks each civilization had available to record what its observers had witnessed. The instrumental seismology that finally formalized this same observation mathematically through Fusakichi Omori's 1894 decay formula and its subsequent refinements is, by comparison, a remarkably recent addition to a much older body of accumulated human attention to this exact phenomenon. Tonight's Kamchatka data, the 11-month-old sequence, the slow decay signature, the four measurable earthquakes of June 19th and June 20th, arriving well outside a textbook standard aftershock window, but squarely within what a high afterslip sequence would predict, is the latest entry in a record of observation that, depending on which of these three traditions one chooses as a starting point, stretches back either several centuries or more than 2.5 millennia. The data is in the record, the interpretation belongs to you. As this report is filed, the ground beneath the Kuril Kamchatka trench remains exactly where it has been for 11 months, an active subduction interface, still working through the aftermath of one of the largest earthquakes ever measured by modern instruments, producing the kind of intermittent, significant seismicity that the mathematics of aftershock decay, formalized more than a century ago and refined considerably since, both predict and explain. We covered a great deal of ground tonight, and it is worth taking a moment to draw the full shape of it together before we close. We began with the immediate instrumental record, a magnitude 6.6 earthquake at 6:52 UTC on June 19th, paired with a magnitude 6 event 1 minute prior and a magnitude 4.9 event 13 minutes after, confirmed independently by the United States Geological Survey, the European Mediterranean Seismological Center, the German Research Center for Geosciences, and Russia's own regional monitoring network. We walked through a fourth event, magnitude 5.8, arriving less than 30 hours later on the afternoon of June 20th. We traced all four of these events back to their origin, the magnitude 8 megathrust rupture of the 29th of July 2025, a rupture so large it sent a tsunami across the entire Pacific basin, disturbed 7 separate volcanic systems across the Kamchatka Peninsula, and physically relocated and lowered the ground beneath an entire city. We examined the mathematics of aftershock decay in detail, explaining why a slow decay signature, the kind this sequence appears to show, indicates extended, ongoing afterslip rather than a closed, settled fault. We place tonight's data within the context of the broader Pacific Ring of Fire and within the specific written historical record of this exact coastline, a record that documents this same fundamental pattern, megathrust rupture, followed by months of significant aftershock activity, recurring at least 4 separate times across nearly 300 years. In 1737, in 1952, in the 2006 to 2007 Olutor doublet, and now again beginning in 2025. And we examined 3 independent ancient and historical traditions from Japan, from the Hebrew prophetic corpus, and from the Hopi mesas of Arizona, each of which arrived centuries or millennia before modern seismology existed, at a structurally similar understanding that an earthquake is the beginning of a process, not its conclusion. There are specific things worth watching in the days and weeks ahead, and we want to name them directly rather than leave you with a vague sense of ongoing concern. The United States Geological Survey's aftershock forecasting model for this sequence will continue to be updated as new data arrives, and any significant revision to the probability windows for further magnitude 6, 0 or greater events would itself be newsworthy and worth tracking through the agency's public advisories. The Kamchatka branch of the Geophysical Survey continues real-time monitoring of the trench, watching specifically for any migration of earthquake depths or any expansion of seismicity into previously quiet sections of the fault, either of which would represent a meaningful change in the sequence's character, rather than simply more of the same pattern. KVERT's daily monitoring of Klyuchevskoy, Krasheninnikov, and Shivaluk remains the most direct indicator of whether continued seismic activity along the trench is translating into renewed volcanic disturbance, the same earthquake-volcano interaction that produced the unprecedented 7 volcano eruption sequence in the days following the original 2025 main shock. The Pacific Tsunami Warning Center's standing protocol will continue to evaluate every qualifying earthquake along this stretch of coastline within minutes of detection, and any future tsunami advisory or warning tied to this sequence specifically would represent a materially different situation from the 4 earthquakes we have reported on tonight, none of which met that threshold. And the broader pattern across the Pacific Ring of Fire this year, the April 2026 Sanriku earthquake in Japan, the June 2026 Mindanao earthquake in the Philippines, and now the continuing Kamchatka sequence, remains worth monitoring as a backdrop, not because any of these events are mechanically connected to one another in a way current science can demonstrate, but because an unusually active year along this chain of subduction zones is itself a meaningful piece of context for understanding any single segment's behavior. There is a broader point worth sitting with before we close, one that extends beyond Kamchatka specifically and applies to nearly everything this channel reports on night after night. The instruments that monitor this planet, the seismometers, the GPS arrays, the satellite-based interferometric radar, the tsunami buoys scattered across the Pacific Basin, are extraordinary achievements of modern science, and nothing in tonight's report should be read as diminishing their value. They allow us to know, within minutes, the precise magnitude, depth, and location of an earthquake occurring on the far side of the planet, a capability that did not exist in any form before the early 20th century, and that has saved a considerable number of lives through early tsunami warning alone. But these instruments are young, measured against the span of time the phenomena they study have been operating. Modern seismology, in any rigorous instrumental sense, is perhaps a century and a quarter old. The Kuril Kamchatka Trench, by contrast, has been producing earthquakes of this general character for as long as the Pacific Plate has been subducting beneath the plates that border it, a span of geological time that dwarfs human civilization entirely, let alone the relatively brief window in which any of it has been instrumentally measured. What this means, practically, is that the written and oral historical record, imperfect, occasionally embellished, filtered through whatever cultural and religious framework a given tradition brought to its observations, nonetheless represents a meaningfully longer window of sustained human attention to this exact category of natural event than the instrumental record alone provides. Krasheninnikov's 1,755 account of the 1,737 earthquake gives us real, specific, datable information about how this fault behaved nearly 3 centuries ago, information that the seismometers simply cannot provide because seismometers did not exist yet. The 3 ancient and historical traditions we examine tonight, Namazu, Isaiah 24, and the Hopi Earth Purification Framework, extend that window of attention considerably further still into a register that is less precise in its specific dating and geography, but no less genuine in its underlying recognition that a major seismic event is the beginning of an espremation, extended process rather than its conclusion. Treating these older traditions with the same careful, source-by-source scrutiny we would apply to a peer-reviewed geophysics paper, asking who recorded the claim, when, under what circumstances, and how it was preserved, is not a concession to superstition. It is simply extending the same evidentiary standard backward across a longer span of recorded human history than the instrumental record alone covers, and it is the standard practice this channel applies to every tradition we examine, in every report we file. We will be watching this specific sequence closely in the days ahead, and if the data changes in a way that meets the materiality threshold we apply before filing any update, a named agency issuing a revised classification, a measurable escalation in scale or frequency, a secondary event directly linked to this one, a revised impact assessment, or substantively new scientific findings that alter the picture, we will file a follow-up report built with the same standard of sourcing and the same refusal to speculate beyond what the data actually supports. Until then, the working picture remains exactly what we have described tonight, a megathrust fault 11 months into a documented, historically consistent aftershock sequence, behaving in a manner that 3 independent ancient and historical traditions working without instruments would have recognized immediately. We want to return, briefly and quietly, to something we noted earlier in tonight's report and asked our audience to hold on to. The instrumental data from this exact stretch of Kamchatka coastline documented something specific and measurable. The ground itself shifted by nearly 20 inches and the peninsula's elevation decreased, recorded by GPS instrumentation operated by a Russian state geophysical agency in the days following the 2025 mainshock. We raise that figure specifically because the traditions we examined in the ancient record section, working without any access to satellites or benchmark surveys, each describes something structurally similar. Not a single moment of shaking that concludes cleanly, but a fundamental alteration in the relationship between land and sea that persists after the visible event has ended. The Namazu tradition frames this as an ongoing thrashing requiring continued restraint. Isaiah 24 frames it as an irreversible staggering and falling that does not rise again. The Hopi tradition frames it as one marker within a larger, accumulating pattern of natural disturbance preceding a complete transformation. None of these traditions had access to a GPS receiver. None of them needed one. The structural insight that significant ground failure along an active subduction interface produces lasting, measurable change rather than a clean return to a prior state was available to careful, sustained human observation long before any instrument existed to confirm it numerically. This is, we think, the actual value of placing tonight's instrumental data alongside this kind of historical and cultural record, and it is worth stating plainly rather than leaving it implied. We are not suggesting that any of these 3 traditions possessed predictive knowledge of the 2025 Kamchatka earthquake specifically, or of the 4 smaller earthquakes we reported on tonight. We are suggesting that the patterns these traditions independently documented, the staggered, extended, multi-stage character of major seismic disturbance, the persistence of instability well beyond the initial shaking, the lasting alteration to the physical landscape, are real patterns demonstrably present in the geophysical behavior of subduction zones like the Kuril Kamchatka Trench, and that multiple human cultures, working independently across thousands of years and thousands of miles, were paying close enough attention to the world around them to notice and record those patterns using whatever language and framework their culture provided. That is not a small accomplishment, regardless of what framework a given viewer brings to interpreting it. It represents, at minimum, a continuous thread of careful human observation of this exact category of natural event that predates instrumental seismology by a span of time considerably longer than instrumental seismology has existed. Tonight's report filed a layer most coverage of this earthquake will not include the full instrumental record, the historical pattern stretching back 3 centuries, and 3 independent ancient traditions that recognize this category of event long before instruments existed to measure it. That combination, agency data married to deep historical and cultural context, is the entire reason this channel exists, and it is not something faster, more reactive coverage is built to provide. We file a new report like this every night on whatever the data shows, and the historical layer never runs out because the human record of watching this planet is older than any single news cycle. If a different event or tradition deserves this treatment, the comment section is the place to say so. We read it. Subscribing costs nothing and tells us the work is reaching the people it is meant for. We continue to monitor. We will report again at last light.